Good morning, everyone present here. And today we'll be looking at a very interesting topic, specifically related to power management. And the question of the hour is, why won't my CPU sleep? So it seems to be a very basic question. It's like, your CPU is not doing any tasks. It's probably sleeping. Well, you would think so, but we'll see why that doesn't always happen. Before we get into the talk, a little bit about us. We are Texas Instruments. We make processors that go into like automotive products to broad market. And we strongly believe in an upstream first policy. So we've always had an upstream first mentality regarding to every open source piece of software that we work with. So as you can see, many of the projects listed here, right from like kernel CI, U-boot, the Linux kernel, or even Zephyr RTOS, we make sure that after we develop the base support in-house, we always try to upstream all of it so that the whole community can benefit from it. A little bit about me. So I'm a power management expert at TI, and I've been primarily working on Arm 64 SoCs for the last 3 years. And I've been a contributor to Linux, U-boot, and ARM trusted firmware as well. Over to you, Kevin.
All right, good morning. My name's Kevin. I'm also doing a lot of work in Linux power management for quite a few years now. And a little bit about my company. So I work for BayLibre for the last around 10 years or so. We're a software services company, and you can read about what we do up there. But for the purposes of this talk, we're here together because we're collaborating closely with Texas Instruments on power management topics. So, all right, so getting into it. So just a little bit of context here. I wanted just to situate what we're going to talk about into the big picture of Linux power management. So this is from a talk I did a while ago on kind of an overview of all of the Linux power management features. And so today we're going to be talking primarily about just this little piece up in here in CPU-idle, and a little bit about suspend-resume type topics as well. So wait, can you see that? There's a laser-looking thing. So we're going to be talking a little bit about CPU-idle, but Linux power management obviously is a very big topic. So I just wanted to remind you that there's lots going on here that we're not going to talk about. We're going to be focusing primarily on idle. So this slide is also from a talk that I did around 10 years ago. So if you want to see it, you can go back and see it. It's surprisingly still up to date. There's a lot of things in Linux power management that haven't changed. There's obviously a lot of things that have changed as well, but from an introductory perspective and a big picture overview, this talk is still pretty relevant. And also, don't miss later on this week, there's another talk on kind of Linux power management features by Theo from Bootlin. So the Wednesday morning at this time slot, there's another good talk on power management, so check that one out. All right, on to CPU-idle. So CPU-idle, the goal of CPU-idle basically is to do nothing, right? But do nothing and save lots of power while doing nothing. So that's kind of what we're talking about here. So, and just as this stuff is kind of a reminder, a refresher. But the goal here is that idle states have this concept of depth, right? So you can be in a deeper idle state or a shallower idle state. These are the terms we use. But that means the deeper you go, the more power savings the chip typically has, but the longer it takes to wake up from those states. And these idle states, there's definitions for them in the device tree, and we'll be getting into the details of that a little bit later. And then how the states actually get entered is pretty platform specific. So today we're going to be focusing a lot on ARM, specifically ARM 64 platforms. Because this is the Embedded Linux conference, that covers quite a bit of what probably many of you are working on. But that's going to be the focus as well today. And then also just a reminder that it's called CPU-idle, but these idle states are not only CPU specific, they can also apply to power domains or clusters as well. We'll get into a little bit of that later. So from the kind of just high-level flow of how CPU-idle works, it all starts with the scheduler. So the scheduler is where the system knows that there's nothing to do, right? When the CPU is idle, and there's nothing else, that means there's no other tasks to run. It runs what's called the idle task. And that triggers an entry into the CPU idle driver. And in CPU idle, there's kind of two parts of CPU idle. There's a kind of a generic part, and then there's a platform-specific part. So the generic part is where it will kind of, there's different CPU idle drivers, but they basically, their goal is to look at all the available idle states in the system and do some sort of intelligent picking of which idle state to enter based on certain criteria. And that's typically how long Linux thinks the system's going to be idle, and then whether it can pick a deeper state, for example, and save more power because it thinks the system's going to be idle for a long time. It may want to pick a deeper state. So those are called, in CPU idle parlance, those are called governors. So CPU idle has a few different governors. I'm not going to get into the details of those, but the basic idea is that their job is to pick the right state for the right conditions, right? And then there's all this platform-specific stuff, and that's what we'll be talking a bit about today. So on ARM64 systems, this actually involves firmware. So in ARM land, this is called PSCI, which stands for the Power State Coordination Interface. And we'll be getting into that in more detail too. But just as a reminder, this is just kind of the big picture for now of how CPU idle is working. So there's also, apologies for this dad joke here. Does anybody know who that is? Yeah, his name's Eric Idle from Monty Python. So I had to throw in because his name's Idle. So apologies in advance for that. There'll be a few of these bad jokes in here, but that's the way we roll. So suspend-to-idle. So this is another. In addition to CPU idle, there's a suspend-to-idle in the kernel, which is a kind of, relatively speaking, one of the newer features in the Linux kernel, but that means it's like 10 plus years old. So suspend-to-idle is actually similar to kind of traditional suspend in the Linux kernel, which is called suspend-to-RAM. So the ways that it's similar is that suspend-to-idle will also freeze all of user space, suspends all the drivers, and can pick states that have memory retention. Memory might be retained, memory might be lost. And it can check for if there's any wake-ups pending and kind of cancel or abort a suspend that's in process. So this is kind of the same thing as suspend-to-RAM. Suspend-to-idle works that. So the way that it's different, though, from suspend-to-RAM is that there's no CPU hot plug in suspend-to-idle. And IRQs are left enabled. So actually, the way to think about suspend-to-idle is essentially quiescing the whole system so that CPU idle can pick the deepest state. That's kind of the simplest way to think about suspend-to-idle. So basically, you're kind of shutting everything down, letting CPU idle governor take over and pick the deepest state. So in suspend-to-idle, that always is the deepest state. There's actually no governors that get involved in suspend-to-idle. And we'll talk about that a little bit later if we have time. And then any wake-up enabled interrupt is capable of waking the system. But of course, there's platform-specific firmware involved here, so the firmware may or may not mask some wake-up sources as well. So yeah, this is just a kind of a quick view of suspend-to-idle. So we want to get right into the first case study and this one's actually based on a true story. So this was on a playboard. I started playing with suspend-to-idle and trying to get it to work, and so this is kind of the story of how that worked or didn't work actually at first. So this Beagle playboard is upstream. So this example is using the mainline kernel and a kind of a rootfs that's pretty minimal build root based system. So there's no, by default, in this upstream device tree, there's no idle states defined in the device tree. So what that means is that if there's no idle states in the device tree, the CPU idle driver will probe but doesn't find any states, so then it just fails. And so then the scheduler, instead of calling CPU idle, the scheduler will default to calling these arch-specific calls. And on ARM64, that just results in the kernel calling the WFI instruction. So it just kind of the wait for interrupt. And so what we see here, so the first thing I notice is I just wanted to see what happens when the system is idle and does nothing. So this is a trace visualization of just sleeping for 2 seconds, right? So what you see here is the system is mostly idle, like you'd expect. There is some background activity happening. There's some IRQs going off because there's network activity and a couple background tasks, but it's mostly idle for 2 seconds here where I traced. So that's good. That's what we expected. We want the kind of the flat spots in the graph mean there's nothing happening. There's only very minimal things waking up, but this is what you expect on a kind of on a system that's just doing nothing. So a quick little aside. So that graph that I showed, so you might be wondering where that graph came. So I'm going to do this very quickly because there's lots of good talks on ftrace and kernel shark out there, but this is just so you know where those graphs came from. I'm using trace command, which is the common tool for ftrace in the kernel. It does all the magic to capture the traces from the kernel and then traces everything and logs everything to this trace.dat file. And then the visualization itself came from kernel shark. So kernel shark is just the visualization tool for that trace.dat file. But there's links here. The slides are already uploaded to the SCED site, so you can look at these later, and these links will take you to other docs. But to continue the case study, the thing that I really wanted to get working was suspend-to-idle on this platform. So rather than just doing sleep, we actually wanted to suspend the system to idle and see what happens. And so this one is interesting because unlike the sleep case, I don't actually expect there to be any wake-ups when I suspend. But here, I'm clearly seeing some things happening when I'm suspended. Right? There's IRQs going off. There's soft IRQs happening. Interesting. I thought of this graph this morning because I didn't sleep that well last night, and this reminded me of my sleep last night. I wanted to be sleeping, but I had lots of wake-ups. But that's what happens the night before I give a talk. So the question now is, right, back to our title, why isn't my CPU sleeping? So these activities that we're seeing IRQs and timers and soft IRQs and so on, like those are all time and timekeeping related activities that are happening. So why are we seeing that when we're supposed to be suspended? Right? The suspended system is supposed to disable these things, and yet we're still seeing them. So the CPU idle path calls this tick freeze function, which is supposed to actually stop timekeeping. But going back to what I said, what I noticed before, that I didn't think about this at the time, but it's become obvious now. But when your system does not actually define any idle states in the device tree, CPU idle driver actually doesn't get registered. Right? So it just calls this default the arch idle function, and it's not actually taking the CPU idle path. Right? So if there's no CPU idle path, there's no S2 idle path, and then there's no tick freeze, which means these timekeeping activities will keep running. This is kind of the first case study because this is the first thing you'd probably run into when you try this on any new system that may not have idle states defined, right? So the solution to this is then, we need to add an idle state to define it, a new idle state in the device tree so that we can actually use CPU idle. So that's what we did here. So Dhruva will get into the details of these device tree in a little bit. But so we added an idle state. We link it to all the 4 CPUs on the system. And this time it's surely going to work, right? Except no. So what we see this time is first some kernel messages, but these messages, the messages that are highlighted there, those aren't coming from the kernel. Those are actually coming from the firmware. Right, and so the firmware now is telling us there's a problem. We just gave it an idle state. The firmware, we passed it an idle state, and the firmware is saying, I don't like that idle state. I don't know what to do with that. Right? So it's just panicking. Right. So and just a reminder, on Arm 64, this is PSCI firmware, right, which is part of the trusted firmware piece, and Dhruva is going to get into that very soon here because, right, the PSCI is telling us it doesn't know what to do, and so we can't enter the state. So the fix for that is actually to add support for these states in the firmware. And so I'm going to skip ahead because Dhruva is going to talk about the firmware in a second, but I'm just going to skip ahead. And so after Dhruva fixed the firmware, this is what we have now in the trace, right? So now we have, you can see for a full 2 seconds now, this is what this is what you want your suspend to look like, right? Between the suspend and resume, there's nothing happening. There's no IRQs, there's no soft IRQs, there's nothing happening. So it's really boring, but this is what you want. You want boring when you're suspending, right? So now let's get into actually how Dhruva implemented the fix.
All right, so from Kevin's talk, we could infer that there are multiple components involved. You can see that it ranges right from across the device tree, the Linux kernel, to the trusted firmware ARM. I won't get into the details of what is the execution levels in ARM, because that's something we can brush over later. But what we need to know here is that Linux runs at an EL1 execution level, and your ARM-trusted firmware runs at an elevated privilege, which is known as the EL3 execution level. And the TFA, or the ARM-trusted firmware, is what implements your vendor sequences. So before we get into all of that, we heard Kevin throw around the word PSCI and power state coordination interface a lot. Let's get to understand what it really is. So from my understanding, it is the one protocol to rule them all. So there is this 100-page document from ARM, which we have linked over here. It's called the PSCI specification, and it's a set of software guidelines and everything related to power management that ARM kind of standardizes. So it includes everything from your core idle management, even the CPU hot plug framework that we have in Linux, that kind of talks via PSCI to the ARM trusted firmware. So whenever you turn on or turn off CPUs, taking them online or offline, that all happens via PSCI. And not only that, even your system shutdown or reset calls actually can go into PSCI, and your ARM trusted firmware can take care of those too. So here's a brief overview of what PSCI looks like in the context of Linux, in the context of TFA. So here on the top, we have the consumer drivers. You have the PSCI SMP, which deals with onlining, offlining CPUs. You have the CPUIdle PSCI. You have the CPUIdle PSCI domains, which deal with all the idle state stuff that we were just discussing. Now, all of these finally interact with the help of the firmware PSCI.c driver, and it uses a transport mechanism to communicate with the ARM-trusted firmware. And via this transport mechanism, we interact with the core PSCI framework, which is inside ARM-trusted firmware. It's inside the lib PSCI folder. And from this core, now you want to expose your platform-specific hooks, because every single vendor out there has very different chip architectures. Everyone has very diverse set of Arm SoCs here. So everyone needs their own vendor-specific sequences. So the lib PSCI offers you callbacks, which you can leverage to create vendor-specific implementations inside the plat folder in ARM-trusted firmware. So let's look at the different ways to do idle using PSCI. There are two ways of doing PSCI idle. There is the standard way, which they call as the platform coordinated way. The reason they call it platform coordinated is because it's the firmware entity that kind of decides on the final idle state. Whereas you have the other smarter version of this, which is called as the OS initiated. So as the name says, it's the OS that is going to be making most of these decisions. So in this case, Linux takes charge to decide which power state transitions are going to happen in your system. The other important thing that you get as part of OS initiated mode is that the whole control lands in the hands of Linux. It's the Linux's responsibility to tell the firmware about which is the last active core and what it needs to suspend and when. Whereas in platform coordinated mode, everything needs to be done at a firmware level. Here's the diagram of how the power state hierarchy kind of looks like. So you have at the top level, which is known as the system level, which encompasses pretty much your whole SoC. Then you have sub part of that, which is the cluster level. Clusters generally include your processing clusters, like if you have a quad core A53 or a dual core A53. These are all parts of your clusters. And then, of course, as part of those clusters, you have your cores. And different entities can enter different types of idle states. So here's how the PSCI implementation looks like inside TFA. How does everything work? How do the state machines work inside TFA? So to understand this, you have to take a look at this very important structure, which is the PSCI power state. The PSCI power state represents your power state parameter. You know, maybe you might have seen the PSCI suspend parameter as part of the device tree in one of the earlier slides. That is the parameter that the Linux kernel is going to pass on to the firmware. So this structure is what's going to remember it. It also contains the array to kind of track what the local power states were across your CPU levels. And the additional thing that you get as part of the OS initiated mode is that it includes the highest level at which your current CPU was active. So here's some of the important callbacks which are part of the core libpsci and which you can leverage as part of your plat-specific implementations. Starting off with the validate power state. The validate power state callback helps you to essentially, it's like your entry point inside the plat folder. That is the first place where your suspend parameter is going to come from Linux. So it checks whether that parameter is valid first of all. It parses that state, and then it converts it into your local PSCI power state that we saw in the earlier slide. The next thing is the CPU standby hook. This will be the most used hook in most cases. So if your system is active, but it has no task to do, most likely Linux will issue this state. So it's the fastest path for your CPU to enter a kind of standby state. Now again, it depends on the vendors what kind of sequence they want to implement, but most of the vendors that I see today just execute the WFI instruction. Then you have a slightly deeper hook. Now let's get into the more latency, more power saving states. So you have the power domain suspend. What this hook is going to help you do, and there are multiple variants of this, so I highly urge you to read the platform porting guide from Arm Trusted Firmware. But what this hook is going to help you do is it's going to start preparing to suspend the system. What we mean by suspend usually is a kind of a suspend to RAM state where it's possible that you may lose context of your CPUs. So it needs to save that state so that it can resume cleanly. And then you have the power domain on or off. And this is related to the hot plug stuff that I mentioned earlier. Whenever you want to turn or take CPUs online or offline, this is the hook where your PSCI calls are going to land in. So you remember case study 1, where we were not able to kind of idle properly? Well, there was this fix needed. What we were doing earlier was we were not setting the core power state properly. So the structure that we saw here was not able to track the proper state machines. And so what we had to do was, if we want to make the CPU idle correctly and we wanted to enter the CPU standby hook, we need to make sure that the validate power state function is properly implemented. So what we needed to do was set that state to the plat retention state. But retention means that it's not going to lose context, so let the CPU just hit WFI. And this fix is now upstream inside Arm Trusted Firmware. I'll let Kevin introduce us to another interesting case study.
Okay, so now that we know a little bit how the firmware is working, we want to add, to support some of these deeper states on this platform. So the next step we went is to add another state, and this is to be one of those deeper states like Dhruva was mentioning. So in this state, the CPUs can actually lose context, right? The CPUs get powered off, context is lost, right? So we add that state in the device tree just like we did with the first one. But notably here, there's another parameter I wanted to highlight. So in this case, this state has this local timer stop flag. So this is going to be important. So this will come up a few times here. But what that means is when the state gets entered, the CPU local timers actually get turned off, right? Because if the CPUs are getting powered off, we don't expect the per CPU timers to keep running, right? At least on these ARM 64 timers. So let's get into that. So one more little aside here. This is a little refresher on how timekeeping is working and some terminology, because this is important, right? So on ARM 64, there's an architected timer. It's part of the standard architecture for ARM 64, and that timer provides two different things. It actually provides a kind of a free-running system counter, and it also provides per CPU timers. Now, in the kernel terminology, we have two different names for these things, right? The free-running kind of continuous counters are clock sources, and clock events are the programmable timers, the ones that we use to program for future events and to set interrupts, right? So you can think of those as like a clock source is kind of like a stopwatch, right? It's just a free-running counter. It's used for time stamping and some basic timekeeping stuff. And clock events are the things that you use to program for future events, right? So, and importantly, also the kernel also has these high-resolution timer API, right? And HR timers are built on top of clock events. So clock events are quite important to what's happening here. And obviously, CPUIdle these are important to CPUIdle because CPUIdle is going to look at when the next event is going to fire, and that helps it decide how long it can sleep and how deep of a state it might entering, right? So this is all just to kind of remind you that clock events are kind of a big deal in clock sources, but especially the difference between the two, these often get confused in the kernel. So think stopwatch versus alarm clock. That's the easiest way I think to think of it. So back to the case. So after we added that idle state to try to hit that deeper state, we noticed it wasn't hitting that state. So we noticed for the firmware itself, the state was never requested from the kernel. And when we looked at the kernel tracing, the kernel was never even trying to select that state. So again, what's going on? Why isn't the CPU actually going to sleep again? And after a fair amount of debugging, which I'll spare you the details, we discovered that, again, it's going to seem obvious saying it after the fact, but it took us a while to find out that the CPUIdle was just refusing to pick our state. And the reason is because the clock event, in this case, at least on this particular SoC, the clock event, the only clock event provider is that ARM 64 architected timer. So if the architected timer is going to be powered off, there's going to be nothing to wake us up again, right? So CPUIdle is noticing that and saying, okay, I see you have a local timer stop, but that timer, that's the only timer I have, so I'm not going to turn off that timer, otherwise we're never going to wake up. Right, so that's what's going on here. The thing is that CPUIdle does it kind of silently. You don't really notice until you trace and notice that your state is never picked. You don't actually notice that's what's going on. So it's like I mean, I like the analogy of the alarm clock again too. Like if you're going to sleep and setting an alarm, but you notice that somebody's going to pull your batteries out of your alarm clock, you're going to want to do something about it, right? And that's kind of what CPUIdle is doing. It's like I'm not going to sleep unless I know I have some way to wake myself up, right? So yeah, so CPUIdle is just refusing, but refusing quietly. So that's why it took me a while to debug that one. So the fix there is if you have a clock event source that's actually going to lose power during the state, this fix is to add another clock event source. So you need to have a clock event source that's going to still be able to keep time and still be able to be programmable during these low power states. So fortunately on these chips, there's quite a few timers on this family of chips. But some of those timers actually get powered off too. But there are some in always-on power domains on these chips. So the good news is that there's an upstream driver for these timers already. But the bad news is the upstream driver didn't actually implement clock source and clock event kind of providers in the driver. So the fix for that was actually to add support to extend this driver that was already there, but just add so that it registers clock events and clock sources. And so after we do that, we know that there's going to be a clock event source that's going to always be on. So even when we hit those low power states, we know that these timers are still going to be on. And if the kernel knows that those timers are going to be on, the kernel actually can switch between clock event sources dynamically on these types of situations. And so CPU idle is one of those paths where the kernel will actually switch from a local CPU local timer to a broadcast timer, and that's what's happening here. So after we did that, it worked. We had our sleep working again. It was hitting the deep state. I don't have any nice visuals here because actually some of the tracing tools for Linux there's no good ways to visualize idle states currently. That's going to be one of the future work topics, but that's why I don't have a graph here, but I can just say that it did work. I assure you that it worked, even though I don't have a graph to show you. So yeah, and that fix is now submitted upstream as well. And so now we'll get a little bit more into the PCI internals for that. Go ahead.
I think I need to learn a little from the CPUIdle framework. I sometimes sleep without setting my alarm, and then I just don't wake up. Okay, so we learned a little about PSCI. Now let's look at how to leverage this beautiful piece of software stack that exists today. Starting off with the device tree. The device tree has these CPU idle states. And for example, this snippet has been taken here from the DT bindings itself. So you can find this documentation in kernel. And you have these states like CPU retention, CPU sleep, and we look at what all of those mean. What are idle states in ARM64 systems? So we have like multiple choices to choose from, and this little graph here helps to visualize the power savings that you get with each kind of idle state. You of course have the running system where you have little to none idle. You have no idle because it's running. But then you have the idle state which offers you a little more power savings. In this case, generally your CPUs or any of your peripherals don't tend to lose context. And then you have the sleep state, where you're most probably going to lose context on your CPUs, on your peripherals. So there's more kind of latency involved in getting up from there. So this is how we describe the device tree idle state. We saw those references to CPU retention or sleep states earlier, but this is more of the elaboration of what they actually contain. So these are some of the important properties that they have. You have the compatible, which of course helps you, determine the drivers associated with that. Then you have the PSCI suspend parameter, which is the important bit that we're going to look at right now. And you can see these weird numbers like 10,000 or some 10100. You might wonder, what do all these numbers mean? So what is this parameter actually helping us to achieve? The reason these numbers are so funny looking is because they're all bit encoded values. These values mean very specific things around whether your CPUs are going to stay on. Is your cluster going to stay on or off? Is it going to lose context? Or does your system need to enter any custom low power modes? Because as we know, all of us with different SoCs these days have a huge variety of low power modes. We have a bunch of controllers suspending. We have, in some cases, even small parts of the SoC alive. So how do you tell that to the firmware from Linux? So here's how we can make some sense out of this suspend parameter. Again, there are two types at this point. You have the original format, and then we have the extended format, both of which are documented in the PSCI spec. Now beware, even though those numbers look random, they are not random. I tried a lot of random combinations and ended up with a lot of crashes. So I decided to dig in. Isn't it just a number that you pass on to the firmware? Why does Linux need to care about it? But no, Linux does do some sort of a validation. So you'll see that there's this function in the kernel which determines validity mask. So it kind of masks with either of these two values, whether it's a valid extended power state or whether it's a valid original format kind of an idle state. So here's how those masks look like. And again, these descriptions are available inside the PSCI spec, but we'll go through the important bits. So the first one, in which you have sort of the FFFF, that helps you identify the specific low power state that you would like to enter. This is the suspend parameter that will get used as the state ID that we talked about in ARM trusted firmware. Then you also have the state type, which is going to be either standby or power down state. Standby means you retain context, power down means you don't. And as part of the state affiliation, it's the level of power hierarchy here that we are going to see. So whether, we saw earlier, there was like a system level, core level, cluster level. This is what's going to help you define that. Now, these are the before and afters of adding an idle state. So without the idle state, as Kevin mentioned before, the driver doesn't even register. So you don't even see that sysfs entry. And then once you do add an idle state, where you would have expected only your idle state to appear, well, kernel has something more it wants to offer. So it also has an in-kernel WFI hook that starts executing. So you end up with two different idle states. And now coming to an even more interesting case study. We have covered so far why my CPU won't sleep. Good, we have our CPU sleeping now. Well, now why won't my CPU wake? Well, now that we are inside idle, our CPU is sleeping. So this is how the talk looked like so far. The user issued an S2 idle. So your user space is frozen. All your tasks and processes are now suspended. You enter the ARM trusted firmware. Your ARM trusted firmware helps you to suspend devices. It puts your SoC in the deepest idle state, all good. And after that, it's time to wake up, and the RTC, or the timer, now triggers an event. But hey, nothing happens. Let's look at why. So here's a brief overview of what's going on inside a typical ARM SoC. So you have here, do I have the pointer? OK. So you have kind of two domains inside our SoC. We have one that is called the main domain, and one that is called an always-on domain. We don't have to get into specifics of how these domains are partitioned, but what's important to know is that in this context, the always-on domain does remain on even after you enter your suspend to RAM. But the main domain is what's essentially shutting off. So once your timer kicked off, this arrow represents it kind of woke up your low-power coprocessor. So you have like this another smaller processor like an M4 or an R5 core, which tries to bring you out of the suspend to RAM state. Now that it's woken up, it knows how to resume your ARM trusted firmware. So it goes and turns on the main domain. It tries to turn on your CPUs. And so TFA here says, hey, Linux, it's time to wake up. But Linux, as Kevin explained earlier, says that, hey, I have no alarm. I didn't get any alarm. So let's just go back and sleep. Why do we need to wake up? So the ARM trusted firmware, like the very obedient firmware that it is, says OK, and goes back to sleep. And that's exactly what was happening on our SoC. So let's try to fix it. Now, there are multiple approaches to this, and this is just one proposition of how you could do this. But what needs to happen is that an interrupt needs to reach your GIC, which is the generic interrupt controller IP from ARM. And this is what triggers the CPUIdle framework's resume logic. So unless and until your CPU that is idling actually gets an interrupt, it won't know that it has to wake up no matter what you tell it. So the fix was that we somehow generate an interrupt to the GIC such that the CPU knows that it now has to wake up. And it also kind of figures out what its wake up source was. Getting to how do you debug these idle states? We have seen so many case studies go so horribly wrong. How do you even go about figuring these issues on your SoCs? JTAG is an obvious choice for most kernel developers. We tend to connect some external debugger, try to attach a core, we try to step through code. But well, it's not always going to work because in low power states, sometimes you tend to turn off your CPUs. So well, what are you going to do? You can't connect to anything. In some cases, let's say you haven't reached that turn off stage and you are stepping and trying to reach that idle hook. But somehow you never get there. Do you know why? Because every time you step, it kind of acts as an interrupt itself. So while you're debugging, it's possible that you're preventing the entry of an idle state in the first place. There's some other ways to debug this. Of course, everyone's favorite. You can add a lot of prints around all the software components, and you can get there as well. But sometimes you have very time-critical stuff which you don't want UART to be messing up. So a little more non-intrusive way could be to make use of the IOs. So in our case, we kind of were toggling the GPIOs to figure out, we have like a 2-core system that we were working on. So one of the CPUs toggled GPIO 1, and the other one toggled GPIO 2. And we ended up kind of putting a logic analyzer to those pins. And we tried to figure out when the CPU was going into idle and when it was not. So we could kind of figure out exactly how much time the whole cluster spent in idling. And here, let's look at some of the trace-based debugs that we can do in Linux.
Yeah, so we already talked about one of these earlier, but another common way of debugging these and tracing this is using the ftrace system in the kernel, right? So we looked at Kernel Shark already, and the other one I wanted to highlight here is a newer UI tool called Perfetto. So Perfetto actually came out of the Android team at Google, I think, but it's kind of browser-based, and you can load trace data into it and visualize it as well. So there's some links to it, and the other talk link here is a really good overview that happened at Embedded Recipes earlier this year, kind of good introduction of how to use Perfetto for the kernel. But also, don't forget to use trace printk. Like, I know a lot of kernel developers don't like tracing, they don't like fancy tools, they just want to debug with printk, right? It works. But printk is not good for low power states because your serial console is obviously going to be turned off, and so you're not going to see your printks anyway. But a trace printk is quite interesting because you can use it just like printk, but it shows up in your tracing tool, so it'll be in your trace buffer, kind of interleaved with all the other trace events. So it's actually quite useful for those of you who really can't give up your printk debugging. I'm in that category too, by the way. So wrapping up here, just the road ahead, I mentioned earlier that some of the trace visualization tools don't do a great job of showing idle states. This Perfetto trace is actually an interesting one because it shows the system is completely idle, but it actually shows the system as actually the CPU is running here. So there's some little bit of debugging we have to do on the debugging tools itself to figure that one out yet. But so there's some little bit of work to do on the visualization tools around idle states. And one of the things I'm really interested in doing, if any of you are into ftrace, I would love to see some work done where we could actually share trace buffers between the firmware and between the kernel. So if the firmware can actually send traces to the same trace buffer that the kernel is using, we could actually use trace tools to get firmware debugging as well, kind of interleaved with kernel tracing. That would be really nice. Also really useful for boot time type issues as well. And then a few other topics here, running out of time, so I'll kind of skip through these. But the last one is important. The last one is the one that Dhruva was talking about, is figuring out exploring the ways to actually wake up and trigger interrupts from the firmware to the Linux kernel is quite useful for these wake up cases as well. So in summary, we kind of went very quickly through a few examples of debugging these situations. There's obviously a lot more that we ran into that we didn't have time for. We can talk about those in the hallway if you want to know more. But the important part here is, like, this is a fairly complex problem because it involves, obviously the complex kernel, but also interactions with firmware. And the firmware is very SoC specific, very vendor specific. There's a lot of this code is in upstream trusted firmware, but there's a lot of it that is in vendor specific code. So it really helps to have good collaboration between the kernel teams and the firmware teams. And that's part of the reason we're doing this talk together, because you really need, like, the kernel teams are often not the same people as the firmware teams, right? So if they're not talking, these problems become even more difficult to debug. So that's that. We can move on to questions. We have time for a couple questions, I think. Thank you. Oh, I guess we're time now. Yeah. Yeah, I think we're at time. So next, yeah. Thank you.